Good morning and welcome to my talk. I realize we're a bit late, so I'm trying to be brief. So I realize also that this is a long title, but the key words here are energy harvesting, which this session is about, and image sensing. Okay, so when I combine these two modalities, I'm Walter Leon-Salas from Purdue University, and it's actually me when I was a bit younger, a few years back. So this is the basic application or scenario where we're trying to provide a solution for. So we have outdoor remote location where we need to monitor, in this case a highway, and we need, for instance, to monitor the traffic on this highway. So we're going to place cameras, sensors along this highway and take pictures as the cars drive by. And of course, here's a remote location, so battery is going to run out. It's very inconvenient to recharge or change the batteries. Or we cannot send a technician every so often, right? So the obvious answer here is let's use energy harvesting. Let's harvest energy from the environment and try to recharge the battery with this sensor. So in this particular application, when we look at the possible sources of energy, outdoors, solar, of course, it has the highest energy density compared to vibrations or thermal. So we decided to go with solar energy. Right? So here what's going to happen is, so we have a sensor, an image sensor, which is exposed to light. And we want to harvest also energy from light. So we're going to merge these two devices. We're going to merge a camera and an energy harvester and come up with a single device that does both. And what allows us to do this is photodiode works, right? So on a camera you have pixels, and each pixel has a photodiode, right? Which we use to sense light. But if you take that photodiode and switch it around, it can work as a solar cell. Right? So you can have tiny solar cells on your image sensor on your camera, and if you want, you can put, say, 50% of these pixels to sense an image, and the other 50% to harvest energy. Right? So that was the main idea. And what allows us to do that is when we look at the IV curve, so current versus voltage here across the photodiode, I want to measure the current through the photodiode. When there is no light shining on the photodiode and when there is light shining on the photodiode, what happens to that? It kind of shifts down when there is light shining on it. Right? And when it shifts down, it creates actually three different regions of operation. One would be the reverse bias region, right? And that will be the region that we normally use a photodiode as a sensor, right? When we want the photodiode to work as a sensor, we bias the photodiode in the reverse bias region. Then we have the forward bias region here. That will be an LED. And then here we have this other region in between the reverse bias and the forward bias. Is called the photo-voltaic region. Interesting thing here is in the reverse bias region and in the forward bias region, the photodiode dissipates energy, consumes energy. But in the photovoltaic region, it actually generates energy, okay? Just because the voltage is positive and the current's coming out of the anode of the diode, so it's generating energy. So that's the principle we're going to use in our camera and to make it work as a harvester and also as a sensor. So when we look at that circuit, we need to if you're familiar with CMOS imaging, you will recognize this as the APS pixel architecture, active pixel sensor. So basically what we do here, we have the photodiode, we reverse bias it, we have a switch that connects it to a positive voltage, so we reverse bias the diode, we charge its capacitance, and then let light, the photo-generated current discharge that capacitance, and then we have an amplifier, and we read out that voltage, right? So that will be a typical pixel design. when we look at the photodiode working as a solar cell, what we need to do is we need to connect it this way, right? The anode to the load and the cathode to ground, right? So when we compare these two modalities, we see that as a sensor, we need to connect the anode to ground, but the cathode to a positive voltage. And when it's going to work as a solar cell, we need to connect the cathode to ground and anode to the output to the load. So we need to switch the pixel, the photodiode around, okay? And so then we came up with this pixel architecture, right? So we have the photodiode here, and we have 4 switches, so H-bridge basically. And so those 4 switches are going to allow me to switch the photodiode around. So when I want it to work as a sensor, I close switch 4 and switch 2, and I have my reverse bias photodiode. And when I want to work it as a solar cell, I close S1 and S3, and I have now the anode available at this EH bus, which is the energy harvesting bus, so I can collect the current from the diode. Okay, so it's a pixel that we need to add a few switches, and then we can have this dual modality. And so we call that a configurable pixel. There are some challenges here, of course. We want to fabricate CMOS, so it can be low-cost fabrication with no extra processing. And so when we look at the standard CMOS, there are a few diodes that we can use. There are N-well, P-substrate, there is PD fusion N-well. We'll have to use PD fusion N-well because we need the anode to be either connected to ground or to the load in this case. So we cannot use the N-well P-substrate diode. We have to use the PD fusion N-well diode. And that creates some problems. And they come from this circuit. So what's going to happen is that I'm going to need a DC-DC converter to boost the rather small voltage that these photodiodes create, right? So they create about 0.4, 0.5 volts, right? That's standard CMOS. And so we need to boost that to maybe 2 to 0.5 volts to power something decent. Right, so when we look at DC converters, this is in this case an ideal one with an ideal input voltage. We see that the DC converter, they share ground, right? Ground of the input source with the ground of the DC converter and the ground of the load, for the most part, right? So when we replace this input source with our photodiode, so then we have to share the grounds. And that's where the problem begins. Why? Because when we look at the actual diode there, we have to use this PD fusion N-well, so we can then connect well to ground or to the output. Then we have this other photodiode here. There's also an N-well and P-substrate photodiode, that's diode D2. That's a parasitic photodiode for our purposes, right? We don't want this photodiode to be there, but it's there. We only want D1 to be there, right? So if we just use a typical connection to a DC-DC converter, what we'll have to do is we'll have to connect the DC converter to ground and also the N-well, which is the cathode, to ground. If we do that, basically what we're doing is we're short-circuiting D2. We're forcing D2 to have 0 voltage losses, right? And D2 is a parasitic photodiode. We don't want the photodiode to be there, but it's there. So what happens when you short-circuit a photodiode? You're going to force it to operate here at 0 voltage, right? And that's when the diode conducts a maximum current. Actually, that's a short-circuit current. So what I'm telling the diode 2, I'm saying by doing this, I'm telling it short-circuit, 0 voltage across U, and it's going to conduct current. So this diode 2 is going to conduct current. It's going to steal current from diode D1, and it's going to lower the current harvest from my pixel. And just to give you evidence of that, and so if we measure the IV curves of diode 1, when diode 2 is engaged, meaning I'm connecting the ground of diode, the cathode of diode 1 to ground, I get this much current. This is the IV curve when I tie the end well to ground. But if I leave the end well floating and measure the IV curve, I get a lot more current. Okay, and that's because the 2 is getting engaged if I connect the cathode to ground. Right? So we need a DC-DC converter that allows me to extract charges from this diode without having to connect the end well to ground or the cathode to ground. So we came up with a solution. We're gonna use a switch inductor. Okay? We could have used also a charge mount, playing with capacitors, but you'll have to use a lot of capacitors to boost the voltage and a lot of switches. So we decided to go with an inductor. I'm going to show you in a minute how it looks like. But before that, let me show you the architecture. So we have a pixel array of these, call them hybrid pixels or configurable pixels. And so we have two buses, the sensing bus and the energy harvesting bus, and goes to the DC-DC converter. This is the layout of our chip. Our first prototype is a small array. It's a 32 by 32 pixels, and each pixel looks like this. This will be the photodiode, and these are the switches and the amplifiers that's in the diode as well. These are some images we capture. These are our setup. Get a little PCB, put the lens on it, and shine light, and so we can capture some decent images. There is some fixed pattern noise if you notice, and that's because we didn't use CDS. This was again our first prototype, and this is the DC-DC converter that we are proposing. So these will be the diodes from the pixels, and these are the parasitic diodes again from those pixels. So what we're proposing is to use a very simple switch inductor DC-DC converter. Have this inductor and 2 switches, and that's all, and a diode. So what's going to happen when the clock is high, switch 1 and switch 2 are closed, and the inductor gets charged by the photodiodes. And again, without having to connect this ground of the load to the ground, to the cathode of the diodes. So this inductor gets charged, and then when the clock is low, this inductor gets discharged to the load and through this diode to prevent current flowing back from the load to the diodes. And so we tested this. We put a supercapacitor here. In place of the load, we put a supercapacitor. I think it was a 0.2 farad capacitor. We tested with a 32 by 32 array. And this shows the voltage across the supercapacitor. We can see that it gets up to almost 3 volts, 2.8, but after 6 hours. So it takes a long time. It's a very small current. We're able to harvest about 2 microwatts from this array. And again, outside, outdoors, no clouds, a lot of light. The efficiency of this DC converter is about 70%. As a conclusion, so we have presented a CMOS image sensor that has dual functionality. It can be used to sense, to capture images, but also to harvest energy at the same time. As a proof of concept, we have what's fabricated. We showed a flying inductor, a switch inductor, DC-DC converter to avoid losses. I would like to acknowledge a fund from the National Science Foundation for this project. With that, I'll